Good afternoon, everyone. I'm very happy to be here presenting to you our latest development. Here in this work, we try to integrate numerical modeling and AI to get some enhancement in the field of 3D concrete printing. So I'll start with a brief introduction on 3D concrete printing. This is a very new technology which can help us to build also organic and complex shapes with a minimum amount of material in maximum accuracy in a very fast times and also minimizing human labor. So you can see that we can really achieve very good structural component, very accurate. But obviously there are a list of challenges to control and govern this technology. And many of these challenges are still not fully answered. But in this talk, I'm mainly focusing on the materials and the process challenges. So let's have a look at some frequent issues that we encounter at the scale of the object. So while we print, we can have failure due to elastic buckling. We can have a plastic collapse. We can have plastic shrinkage causing cracks, which is going to ruin the quality of our object. And finally, we can have weak bonds. So between the layers, we can have a very bad joining. Okay, so then we have a second series of problems which are more at the scale of the filament. So we can have filament tearing if we print too fast or the material is not fluid enough. Then we can have uneven layers quality. We can have under extrusion or over extrusion, which are all different kind of problems. So what are the solutions? Well, mainly what is done until now is trial and error solution. So you try until you get the best performances. Then you can also try to help yourself with some experimental tests that can guide you a little bit more, but still they are limited. Then there are numerical simulations which are very good. They can help you predict in advance the performances and the quality of your extrusion process, but they are still under development. So, and finally, we can have censoring, and also with the idea that maybe in the next years we are going towards digital twins, and this will further enhance the possibilities. So what's the idea of this talk? We came up with the idea, why don't we try to combine tools that are already available in this moment to create a framework that can help us to optimize the printing process, increasing reliability and accuracy, and also it can help us to develop new mix designs. For example, if we want to address the fact that we want to create more sustainable mixes or more durable mixes, we need to work on them. So how can we do this? Well, this is, I think, the key scheme of the presentation. So in the next slide, we are going to see it more in depth. But the basic idea is let's say that we want to develop a new mix design, a new 3D printable mix design. We start with a tentative mix design. Maybe we perform some text and we get a tentative rheology, so a yield stress and a viscosity value. Then we can put some tentative printing parameters, for example, a velocity of the printer or the extrusion velocity and so on. And we can perform numerical simulations. And then we can evaluate the outcome in the numerical simulation. So let's say if we are not happy with our outcome because, for example, the layer is not very good, or maybe we notice any kind of problem, we can go back in the loop, change the rheology or change the printing parameters until we are satisfied. And once the outcome evaluation is okay, then there is the last phase, which is from the rheology, we want to go back to a mixed design, which is actually creating or which is actually associated to the material parameters. So let's see it more in detail that it will be more clear. So first of all, we want a simple experimental test which can in a very fast way tell us some information about the yield stress of a certain cementitious mix. And why the yield stress? Because it's for sure the most important parameter in 3D concrete printing. So here are the results that we have in a flow table test. So basically you perform something similar to a slump test, and then you start vibrating it, and in time it's going to spread over this table. And then there are in the literature some formulas which allow us to correlate the spreading with the yield stress of the material. And then we can get some interpolation and extrapolate back the value of the yield stress. So you see it's quite a fast experimental test. Then, second step. Once we have an idea of the yield stress, and maybe also the viscosity, we need to set some printing parameters. So the nozzle velocity, the extrusion velocity, the nozzle diameter, the height of the nozzle from the ground, and these parameters are controlling the process. So with the set of material properties we have defined and these printing parameters, we can perform a numerical simulation. What are the available tools? Well, different methods are under development. In this talk I will focus on fluid models, which is the one that we have been developing. So in a fluid model, the fresh concrete is treated with Navier-Stokes equations, which are coupled with the model for the material behaviors, and for concrete we can use, for example, the Bingham law. And you see that the yield stress, the yield point, is the main feature of this constitutive model. And then we have some finite element discretization of these equations that allow us to perform the simulations. So to prove to you that this numerical model that we have been developing works, we show the validation. So we can try to print some filaments with different printing parameters, for example, different velocities or different height of the nozzles. And the geometry of the filament we obtain in the simulation are compared to the experiments in terms of the cross sections. So you can see that numerical simulations are able to give very accurate description of the real geometry. So once the tool has been validated, we can use it to operate and try to change the material properties to see if we can improve the layers quality or if we can control the geometry. So here I can show you something like a parametric analysis in which we change the value of the yield stress, and a wide range of different geometries can be created. Okay, so maybe also this slide can show it better. You can see really the change in the filament cross-section due to the changing in the yield stress. Here we are instead trying to change the printing velocity, which is another very important parameter, and you see that in this case it's even more important to understand what is the good printing velocity, otherwise we can have problems like filament tearing and uneven layers width. Okay, so finally, once we find through the numerical simulations the optimal printing parameters and the optimal material parameters to create a certain filament geometry, the last issue to be addressed is how can we go back from the material parameter to a certain mix design. And this is quite a difficult question to be answered, and this is why we have decided to try to answer it with a neural network. What's the idea? Basically, we would like to go from the yield stress back to the composition of the mix design. But this is not very easy because there may be multiple mix design giving us a certain yield stress. So we reverse the problem and we say, let's try to create a neural network that, given a certain mixed design, will tell us what the yield stress is. So this is, the neural network here is used as a very fast tool that can help us to assess a certain mixed design. And so that the designer can use it, make some attempts until he finds a certain composition which goes very near the yield stress that we want. Okay. So how does the neural network work? We have some inputs. For example, we selected, in this case, something like 10 inputs. And the inputs are the components of the mixed design of our cementitious mortar. And then the neural network is trained in order to correlate for given sets of design parameters with the yield stress. So, well, now I'm not going into detail about how the neural network works, but the idea is it works similar to an interpolation. So we give them, you have this value, W, which are the weight, and during the training phase, the weights are calibrated to give the best interpolation of the input data. So you can see here that we have a certain number of, for example, mixed design, which are taken from the literature, and for which we know the associated yield stress, for example, from experimental tests. So we divide it in 3 sets, the training set, the testing set, and the validation set. And then firstly we start the training until we get some interpolation. Then with the neural network that has been trained, we start validating the results. And finally, we can test the performances to see how the neural network is able to predict new values which has never been seen before. So obviously this part of the neural network is still under development. Is also the work that a colleague of mine, Andrea Marcucci, is working on. And the main limitations is, I think as in the first presentation of this session was mentioned, the lack of data, because we have like for 3D printing the set of mixed design and is still quite limited, and not always they are shared. But anyway, the neural network showed that in the preliminary results it can achieve some good performances, and obviously we can work to increase them. Okay, so thank you all. Okay, before stopping, just something about future works. So obviously, as I was saying, increase the performances of the neural network to make it more stable with respect to the fact that we have a limited amount of training data. And also in the future, one can think something similar, not only to assess extrudability, but also for buildability, so multi-layer printing. Okay. So, forgot the video here. When I mean multi-layer print, I mean assess also the performances when we print more layer one on top of the other. Okay, so that's all. Thank you all for the attention. If you are interested in the numerical model, we have already started publishing about it in this article. And if you have questions, I'll be happy to answer.